So first, we're going to talk about electrophilic addition reactions, which include the reactions of alkenes with hydrogen halides, and then the reaction of alkenes with water, which is acid catalyzed. These occur because we have a double bond between two carbons. Now, we have pi bonds where the electrons are actually hanging out pretty far out from the nuclei. So we've got this area with significant partial negative charge, and that's attracted to the partial positive charge of the hydrogen on a hydrogen halide, or later the hydrogen on a hydronium. And so you see that this allows for the addition of the hydrogen and the other part of the molecule to both carbons of the carbon-carbon double bond. So in the most basic form, take our 1-propene, and you'll be adding a hydrogen to the less substituted carbon, the one with more hydrogens on it, but less alkyl groups on it. And then adding the other part of the molecule, the bromine, to the more substituted carbon, the one with more alkyl groups on it and fewer hydrogens. And so the H is going to go here, and the bromine is going to go here. And so you can predict the products. The bromine ends up on the more substituted, more central carbon. We get this type of reaction where with the bromine going to the more central carbon because of the following mechanism. Yes, this double bond attacks this hydrogen, and I'm showing the electrons moving here towards that positive charge. And that's going to form a new bond with the hydrogen, which because hydrogen can only have 2 valence electrons around it and not 4, will cause this other bond to break, and the electrons in that bond will go towards that bromine. And so now the hydrogen is going to end up, you have to choose between these 2 carbons. It's going to end up on the one with more hydrogens on it. So that hydrogen was just added here, and that's going to leave a carbocation, this absence of the lone pair of the electrons there, leaving a positive formal charge on the carbon. That carbocation is more stable on this more substituted carbon, the one with this other alkyl group on it, because the alkyl group actually donates a little bit of electron density towards it, reducing the positive charge there and pulling some of the positive charge towards this carbon. So yeah, the positive carbocation ends up on the more substituted carbon. And now we have our bromide left over. This is negative, which is attracted to the positive carbocation, and hence its lone pair of electrons attacks that carbon, forms a bond. There is your new bond. So reactions like this follow Markovnikov's rule, which says that if you're adding a hydrogen, it's going to add to the carbon, the double bonded carbon, that has more hydrogens on it. And so the other thing, whether in this case a halide or in the next case an OH group, is going to add to the other carbon, the one where the carbocation would have been more stable, the one that is more substituted with carbon alkyl groups. All right, so the other type of electrophilic addition is an acid-catalyzed hydration. In this case, a hydrogen will attack and attach to the other carbon of the carbon-carbon double bond. It will attach to the carbon with the more hydrogens on it, and you'll be adding an OH group to the other carbon, which is of the carbon-carbon double bond. So OH group here on this carbon, an extra hydrogen on this carbon. So why does this occur? Well, here is our pi bond, which is fairly electronegative in that it has a lot of negative electron density floating out here away from the nuclei. It attacks this hydronium, which we have because we have sulfuric acid in water, providing hydronium ions. So it attacks this hydronium. Hydrogen can't have 2 bonds on it, so one of the bonds, the electrons in it, moves on to that of water. So now, that hydrogen ends up on this less substituted carbon. There it is. We're left with the carbocation on the more substituted carbon. And now one of these waters hanging around is going to attack that carbocation. The oxygen of water is relatively negative. We've got negative lone pair of electrons here, which is attracted to the positive charge of the carbocation. So we form a new bond with that lone pair of electrons. You can see that here. And now, to finish up the reaction, another water molecule at some point will come by, grab that hydrogen of this ion, the lone pair of, and then the electrons in this bond will end up back on oxygen, and we'll be left with an OH group on this carbon. So we have formed an alcohol. So these are the electrophilic addition reactions. Another type of reaction is a nucleophilic substitution reaction, where a nucleophile will substitute or replace a leaving group on an alkyl group. So a nucleophile is something which loves a nucleus. It loves positive charge. So for example, this methoxide here, it's got a negative charge on the oxygen, and that's going to be attracted to the relatively positive charge on this carbon, which is caused by bromine pulling electron density off of it. And so this oxygen being attracted to that positive carbon is going to attack it and drive the bromine off. And so you'll be replacing that bromine ultimately with this OCH3 group. So you can see the mechanism here. Here's our OCH3 minus ion floating around. It attacks that relatively positive carbon, and carbon can't have more than 8 valence electrons around it. So it had 2, 4, and then another 4 hydrogen electrons by the hydrogen here. It had 8, so if we're going to form a new bond towards it, we're going to have to break a bond. And so that forces this bromine off. Those electrons in this bond are broken and move towards the bromine. And so we have this new structure. So some common nucleophiles which will attack the alkyl group include things like bromide and iodide. They're negative, and they have electrons kind of far from the nucleus. These are polarizable ions, so they're easily able to kind of reach in and attack the relatively positive carbons. We also have things like hydroxide or methoxide. Again, we have negative charge, which is unstable in this case, so it's likely to react. And then finally, we even have not negative ions, but just molecules like water or methanol. They've got oxygens which have lone pairs of electrons on them. They're relatively negative and will be attracted to relatively positive carbons. And then later you'll have leaving groups, things like iodide, bromide, chloride, hydroxide, and amide. These are able to leave more easily if they're more stable. There's increasing leaving ability as you go up. Just as over here, there's increasing nucleophilicity, ability to attack the alkyl groups. Thanks for watching.